All right, so we'll start. Good morning, everyone who is connected. So today is the last lecture of the course of Introduction to Artificial Intelligence, and our last topic for this final course, for this final lecture, will be Artificial General Intelligence. So today's lecture, I would start basically with a disclaimer, which is to say that today's lecture will be much less technical than all the previous lectures we had and much more speculative, right? And so we'll try basically to answer or to give some first element of answers as to how one could build agents that would be what we call generally intelligent. And so we'll first start by defining what we mean by artificial general intelligence and how it is different from everything we've seen during this course. So we'll basically go back to our definition of AI itself. And then I will walk you through a few hypotheses, working hypotheses that researchers are working on towards building this artificial general intelligence. So we'll first cover a theoretical mathematical formalism, which is known as AIXI. And you will see that even though it may look a bit complicated, it's actually including and generalizing many of the things we have seen together. And then we'll talk briefly for the second part of this lecture about artificial life, which is a way, basically, an algorithmic way to replicate or to resimulate evolutionary processes with the working hypothesis that eventually, starting from simple building blocks, that evolutionary processes should lead to creatures or agents that are somehow intelligent. And so we'll see how they work and the kind of results we can already achieve today. And finally, of course, I will conclude with a few more general words about the course itself. All right. So we have been talking a lot, and I've been showing you a lot of videos about, for example, AlphaGo, self-driving cars, and many other quite exciting technological breakthroughs that exist today, right? They are not science fiction. And so already today there are many interesting applications of artificial intelligence. However, now you should understand that when it comes to the details and how these techniques are implemented, you understand quite well that none of them would lead to agents that are, for example, self-aware or that would decide to kill humanity, right? And so we go from technological breakthrough to basically press coverage. So the depiction of AI in the media is quite different from the technical reality, I would say. And this is something that now I hope you will be aware and you will pay attention to, and you will be able to explain to others that we are really very far away from having this kind of Terminator-like agents that would become self-conscious, that would dominate humanity and all these science fiction stories, right? What really you should have in mind when it comes to AI, or at least today's artificial intelligence, is this picture of the washing machine. In the sense that today's artificial intelligence remains narrow, meaning that the AI systems that you can build, indeed, many of them will reach superhuman level performance for the task, on many tasks, like computer vision, playing games like the game of Go or the game of chess. Very recently, a few days ago, there was a huge breakthrough which was announced about protein folding, where huge progress was made thanks to artificial intelligence. But all these techniques, even though they are really breakthroughs by themselves and they reach superhuman level performance, they only work for very specific problems, right? And so they do not generalize to other tasks. If you take a system which was built to do some specific task, you will not be able, of course, you won't be able to reuse that same system to solve a different task. If you take a washing machine, it can wash your clothes very well, but it wouldn't be able to play the game of Go or the game of chess, and vice versa. You can take a very smart agent that can play chess or Go or Pac-Man, one of yours. It won't be able to solve to drive a car, right? And this is something we would like in the end maybe to achieve, or try to basically expand our definition of artificial intelligence to agents that would not only be good at some specific task, but would be able to generalize to tasks for which they were not trained, right? And so this is something we can do as humans. We can do many things, and you can also solve new tasks that you've never seen before, or at least you can learn to solve them. So this is the kind of maybe goal we would want to reach when it comes to artificial general intelligence. So as an example, I will take the case of AlphaGo. So AlphaGo is this computer program which was developed a few years ago, and which basically defeated human world champions at the game of Go. So this is something which for long was thought to be beyond reach. The scientific community in AI thought that it would take a few decades to be able to eventually have an agent that would play that game quite well. And the reason is that simply the sheer number of combinations of different games and the number of actions that you can take at every step is so large that algorithms that we have seen, for example, together would basically collapse. They would be impractical because the state action space is simply too large. But a few years ago, we were proved otherwise, and using deep learning techniques and Monte Carlo research, the team at DeepMind managed to build these agents and to reach superhuman performance at the game. However, when you look closely, even though this is a huge breakthrough, that game has a few and key convenient properties. So the first one is that that game is deterministic. So there is no noise in the game. If you start in a state, you play some action, you take some action, then the outcome is perfectly defined. There is no uncertainty about that, right? It's also fully observed, meaning that each player has complete information. There is nothing which is hidden to the player or only known to some of the players. The action space, even though it's large, it's still discrete, meaning that there is always a finite number of actions which is possible, and you don't have, by contrast, you could have a continuous action space instead. You also have a perfect simulator, so you can perfectly reproduce the game engine in this case. Usually the episodes are quite short. I mean, it depends what you mean by short, but it's a game usually would last for 200 actions, maybe a few more, maybe a few less. But you would not have to take tens of thousands of actions as you would do, for example, when it comes to drive a car from one city to a destination. Also, the goodness of an agent is clear. It's whether or not you win the games, right? So this allows a clear and fast evaluations by just following the rules of the game. And also we have data. right? And this is something quite important. We have access for this game to a huge data set of games. For example, all games that were played by professional players are of course recorded and put in databases. And this is this in itself is some precious information that you can then leverage and use to try to bootstrap and learn an agent quite well. Now, the question would be, could we run the same agent, the same AlphaGo agent, on a robot for this Amazon picking challenge? So the Amazon picking challenge is basically a challenge in which you have a robot, that robot in blue, and that robot is some kind of warehouse, as the kind of warehouse you could imagine at Amazon. And the goal is to basically give the robot a list of items to find and then put in some basket, right? Like one of these baskets that you see in yellow. So this task for us is quite easy, and it looks much easier as the task of playing the game of Go quite well, right? But for an artificial intelligence agent, it's actually much more complicated, at least given the algorithms and the techniques that we have today, right? The reason is that if we compare the properties of this challenge, of this setup of this task to AlphaGo, right? We don't have the same convenient properties. So that task, that environment is still deterministic, so that's convenient. However, it's not fully observed. So for example, the robot could have some camera which is put on itself, or which is static in some place of the warehouse, but this would give to the robot only partial observations about the whole environment. For example, if the robot is to pick some item, it does not know in advance what will be behind this item. The action space is discrete, so that's still convenient, even though you could maybe argue that when it comes to defining the position of the joints in this robotic arm, it's almost as if that was continuous, or at least you could view your discrete action space as some discretized versions of a continuous action space. But still, we could assume it's discrete, so that's still fine. The main issue, however, I would say, is that we don't have access to a perfect simulator, right? We cannot simulate reality in a computer. We can maybe try to reproduce it quite well, but so far there is still a huge simulation to reality gap which is still so large that anything you would learn in simulation would not be able to generalize to the outside world. And that's a huge bottleneck. That's a huge problem that we have so far when it comes to learning these kind of agents that you would like to deploy in the real world, but you don't have any simulator of the real world. So you could say, maybe I would, fine, then I would just learn my policy, for example, as we have seen last 2 weeks ago with reinforcement learning algorithms that I would run directly in the real world. The issue is that you would need to run this algorithm for very long, and you would have a huge bottleneck because you would have to actually play these things in reality, and this would take time. And you would need, at least for this kind of deep reinforcement learning algorithm to work, you would need in the order often of thousands or tens of thousands or even millions of interactions with the environment before you start learning a good policy. And that's something which is simply not possible in reality, because it would just take months or years for the robot to learn anything. And of course, the robot could even break, or it could break the environment. And so you can quickly understand that it would just be impractical to try to learn a policy directly in the real world. Then the episodes themselves, they are not as short as episode that you would have in AlphaGo, because you would have to define what you have to, which actions you have to take at every time steps. And again, if you consider discretizations of time, could have, I don't know, maybe 30 actions per minute, per second, or per minute, I don't know, or 1 action every second, or maybe 5 every second, I don't know what's reasonable. But then, let's say 5 actions per second when it comes to move the arm. And then a full interactions to collect a few, let's say 10 items in this warehouse, maybe would last for 10, 15 minutes, 30 minutes, I don't know. So if you multiply this with the amount of actions that you would have to decide at every second, then you get a huge sequence of actions that you would have to determine in order to solve the task in the thousands or tens of thousands of actions. And this is much more difficult than dealing with very short episodes. We have also the issue of evaluating the goodness of the policy we would learn. So one of the main tasks, for example, in this speaking challenge is just to be able to grasp an object. And of course, there are many ways you could grasp an object, and which one should you prefer is not clear, and the evaluation would not be something you can directly program in a computer. So for example, you could try to seize, this is my phone, you could try to seize it maybe like this, but this is something you would not do as a human, because you would know it looks very unstable, and if I move quickly, maybe my phone could just fall off and break. And so maybe you would prefer a good grasp for which you know it's very unlikely that the phone would fall. But this is something we know, but which is quite difficult to express, and which we cannot evaluate directly by a function. So the evaluation is itself quite fuzzy and vague and difficult. And of course, if you don't give back good learning signal to the agents, how could it learn? So that's a tricky problem. And then finally, we don't have a huge data set for this problem. And so it's much more difficult to bootstrap the system, which would be already quite good, and then to make it even better, we would basically have to learn from scratch, or maybe just from a few tens or hundreds of samples. So that's much more complicated when it would come to implement this task or by a computer program, even though as a human, for us, it's something we do naturally, and which we are good for, and we are, of course, not as good, at least not all of us, when it comes to play the game of Go. Yeah, so there is an interesting question in the chat. So you could use, how do you say that in English? Ventouse. So you could change basically the way you seize the object, and so you could replace the hand or the gripper with some other device. Of course, you could do that, but then you would put your own human knowledge into the robot. And so maybe that's something. I mean, if you want eventually to make a robot which is generally intelligent, it should be able to properly make use of its own body, regardless of how complicated is that body. So we are using hands, and we managed to use these hands even though they are made of I don't know how many bones we have in a hand, but it's several dozens, I suppose, and then many different muscles in this hand, and so in the end it's quite complicated actually, but still we managed to control it very well. So of course you could simplify the hand with something which is very simple and then easier to control, and that would certainly work better in the short term. But if then it would come to, okay, we could grasp the object, but if then what we want to do is to manipulate the object, so then what we want to do is to manipulate, so to be able to, I don't know, move the position of the object that we've grasped, then we would need something which is better than just a simple gripper. So my point, and there is another question, it's not to simplify the task for the robots, right? My goal would be to, okay, this is the task, and maybe we could make it simpler for the robot, but that's not today's question. What we want to answer instead is, given a task, can you make a robot or an agent which would be generally intelligent and which would be then able to solve this kind of task? So, second question, why is it not viable to train robots in real life during years? We train baby humans during more than a year in order to only walk. Well, that's, you could try to imagine that, but you would need to be very confident about the learning algorithm that you use to train them, because if you notice that after a few years it does not work, you would have to start again, and you would not have many trials at your disposal to adjust the learning algorithm. So there is simply cost. So it's quite expensive to build this robot or to buy these robots. And they might just break, so you may train them maybe for a few days, for a few weeks, but there is no guarantee that they will function properly during years. And so you would have to deal with that. And you would, of course, they are expensive by themselves, so you would not be able to buy hundreds or thousands of them. Maybe you would have one or two, or maybe a few tens if you work at a big research lab, but no more really, no more than that, at least with today's technology. All right, so let me go back to artificial general intelligence, and I would define it basically. So artificial general intelligence is also known as AGI. And we could define it as the intelligence of a machine that could successfully perform any intellectual task that a human being could perform. So this is very broad and quite similar to the definitions we discussed about in the first lectures of the course. And indeed, there are, I mean, when you think about it, if you want a machine to be able to successfully perform any intellectual task, at least as good as any other human being, then that means implicitly, and this is something we agree on in the scientific community, then that machine, that agent, should be able, in some way, we don't know how, but it should be able to reason, maybe to use strategy, to solve puzzles, and to plan. And this is something we've talked about at length in this course. We've seen algorithms to implement all these things, but always for specific tasks. We've also, this machine should certainly then be able to make judgments under uncertainty, and that's something we have also seen, how to deal with uncertainty and reason under this uncertainty. It should also be able to represent knowledge, including common sense knowledge. It should be able to improve itself and to learn new skills. It should be able, of course, to communicate in natural language if you want this agent to interact with us. And this is really the last point, which is important. That machine should be able to integrate all these previous skills together towards a common goals, or towards common goals, right? And so, really the key difference is that we want all these things without defining a priori what is the task that we want to solve. So this is similar to our definition of thinking rationally, but as I just said, applied broadly to any set of tasks. And this set of tasks is not known in advance. While, for example, in all the algorithms that you have to implement, you knew that your Pac-Man agents has to collect all the food dots, maybe the capsules, and to avoid the ghost. And you knew that in advance, and that helps a lot. That helps you a lot to implement good enough agents. But it will be a quite different story if you want then to implement an agent that should play that game quite well, but maybe other games and solve this challenge, for example, as well. So that's basically an open resource question, and we don't know how to do that, to be honest. And we don't know when we'll have elements of answers that are convincing enough as a research community, as a scientific community, we don't know how we should approach AGI, how should we try to tackle this problem, and it's very speculative when we'll start having good elements of answers to these questions. So there are several working hypotheses. So one very strong hypothesis is to make use of learning algorithms, so we have seen a few together, supervised learning, reinforcement learning we talked about briefly. But there are other paradigms like unsupervised learning and a few others. And progress in this field is very fast. And this is really this field, machine learning, deep learning, which has led to the latest breakthrough that we've talked about together. And it seems that if we continue pushing further the field, then maybe we'll start having AGI, even though this is still very far-fetched, and we have no convincing agents that would be able to generalize across tasks. So maybe in 10, 20 years from now, or much later, we don't know. So I will not talk about this one today because we have already had a lecture or 2 lectures on learning, and you will have many follow-up courses in your master program if you're interested by this topic, like Introduction to Machine Learning, Deep Learning, and a few others. What I want to talk about today are 2 alternative approaches or 2 alternative hypotheses. The first one is a mathematical formalism, which is known as AIXI, and the second one is artificial life. And again, I want to stress that these are just working hypotheses. It's very likely that none of these 3 approaches will lead to AGI, and maybe it's something else, another very good idea that will prove to be effective and lead to this kind of generally intelligent agents. So this is why I was also saying today's lecture is quite speculative because we are really at the boundary of here today of artificial intelligence, and we don't know what will happen in the future. All right, so let's start with the first one, AIXI. So AIXI is a theoretical framework which was proposed now 15 years ago by Marcus Utter, and it's a theoretical mathematical formalism of artificial general intelligence. So let's see how that works. So it's basically a combination of many principles we have seen together that are all mixed in order to have some kind of universal agents for decision-making processes. So the first principle that is formalism is based on is the Occam's razors principle, which is this simple idea that, okay, for example, let's say you want to build an agent, but that agent in the first place will not know in which environment it is in, right? And what is the task that it should solve. So that principle says that among all the hypotheses of environments, you should prefer the one which is maybe the simplest, right? And you would have to define what you mean by simplest. The second principle is what is said by Epicurus, which is to keep all hypotheses that are consistent. Not only you should prefer the simplest consistent hypothesis, as said by Occam, but maybe it would be wise to keep all the hypotheses that are actually consistent with the data that you've observed so far. And then if you mix these two things together, then you arrive to the Bayes rule, again, which you can view as, okay, at the same time, I will keep all hypotheses that are consistent, and I will represent that by a distribution over hypotheses. But I will still give some preferences to some of these hypotheses. And this is what you would do also when you define a prior on your hypothesis. This is precisely when you will say, okay, this hypothesis is more likely than this other, right? And this is how you could implement concretely this definition of simplicity of hypothesis, while keeping all of the hypotheses that are consistent, right? And the consistency with the data would be in this case measured or instantiated by the likelihood of the data P of D given H, right? It says that if I suppose this hypothesis H, then I can determine what's the probability or the density of the data that I observed. And if it's very low, that means that hypothesis is inconsistent with the data. On the other hand, if this is large, then that means the hypothesis is consistent with the data. The next principle is given by Alan Turing himself, which is this idea that it is possible to invent a single machine which can be used to compute any computable sequence. And so this is something you will see later on in your master program, at least for those of you that will graduate in computer science or computer engineering, and which is this idea that a Turing machine is some kind of universal computer which is able to basically reproduce any kind of program, right? And that computer, that simple computer, is a single and universal machine by itself. And then finally, the last ingredient to this framework is Solomonov induction, which is to say that what we'll do is that we'll represent our hypothesis that we have about environment, about task, as computer programs, right? And so we'll use computer programs mu as our hypothesis. And then we'll make a weighted prediction based on all consistent programs, which are programs that should be weighted higher. That means we'll basically use the Bayes rule and instantiate this H hypothesis as computer programs. And what we'll say is that computer programs that are short, right, will have a higher prior beliefs than programs that are longer. Now, if you mix all these things together, what you arrive to in this framework is this formula. So you have this notation epsilon of pi, which basically defines what is the universal intelligence of some agent pi, right? Where this agent pi, in this case, would be represented by the policy of the agent. And this epsilon pi, this measure of universal intelligence, is defined as some weighted combinations of some v values. And so this v value is exactly the same as the kind of v values we have seen before. So v for the policy pi in some environment mu is simply the expected sum of future rewards, or you could also discount them if you want, when the agent pi interacts with the environment mu. Right? Mu is the environment of the agent, which you see appearing in the V notation. And this environment is itself represented as a computer program, and it belongs to a set E, which is the set of all computable reward-bounded environments. So you would be dealing with a gigantic set of possible environments, and which would be a set of computer programs that represent the environments, right? And then what you would say is that, well, I will define the measure of intelligence of my agent pi as basically the weighted reward that the agents would get in all possible environments, right? And of course, I would not prefer equally all environments. I would favor environments which are short, which are simple, right? And this notion of simplicity is what is defined by this notation K, which corresponds to the Kolmogorov complexity, which is basically a measure of complexity of a program, and we measure it in this case as the length of the shortest universal Turing machine that would describe that environment mu, right? So you could, if you don't know what is a Turing machine yet, it's fine. You could just view that. You could just say, okay, I could describe an environment in my favorite computer programming language, let's say Python, and so I could have many different programs, Python programs that could describe the same environment, and among all those different programs, I would pick the one which is the shortest, and the length of these shortest programs would basically then be a measure of the complexity of the environment, right, that I'm representing with this program. So if that complexity, if the dat length is short, then that means the complexity is that the environment is simple, and vice versa, right? And so you would reweight basically these v values depending on how simple are the environments. If they are simple, you would put more weights. If they are very complicated, then maybe they are not that important. That's your prior belief. They will account for less in this formula. Right. So this is in a single in a single equation. What we've just defined is a measure of universal intelligence, and this measure is specific, of course, to some policy pi, right? So now, if our goal is to find the best of all this, an agent which would be the most intelligent according to this definition, then that means simply what I want to find is the policy pi for which epsilon is maximum. And this is basically this AIXI agent that the framework is defining. So the policy pi for which epsilon is maximum is our perfect theoretical agent. So that's basically an agent that would perform as optimally as it can on all possible tasks that you can describe as computer programs. So this is a nice framework. Now let's maybe see if there would be a way to actually find this pi AIXI agent. So let me rephrase. So, or rather, let's see how this agent would work if we wanted to implement it. So the first thing is that let's assume that you put this AIXI agent in some environment, and of course this environment is unknown to the agent. But the agent can interact with the environment, and so could collect data about it. It can collect observations, and then from these observations, it can then keep or basically narrow down the set of environments that would be compatible with these observations, right? So if we go back to our formalism, that would mean that that theoretical agents would like to basically know in which Turing machine it's currently living, right? In which computer program in which computer program he is currently in, right? Because if it knew that, then it could plan perfectly. It would just use one of these reinforcement learning algorithms, and we've shown that, I've told you that some of them are optimal, and that would be the end of the story. But the agent does not know that, right? So what he will do is that it will use the Bayes rule to update its belief given its experience, right? So the agent would start with some prior beliefs that you define on all computer programs or on all Turing machines. You would put more weights. You would prefer Turing machines that are simple over the ones that are quite complicated. And so this is what you see with this histogram in pink. And then the agent would start interacting with the environment, would collect observations, and then by applying the Bayes rule, it would reweight basically these prior beliefs depending on the likelihood of the data given the environment, the corresponding environment, right? And so you would have then this likelihood term, which basically assess which of these Turing machines, which of these computer programs are consistent with that data that the agent has collected. And now if you multiply these two things together, you have a quantity which is proportional to the posterior density. So of basically your updated beliefs about the consistent environments. Now that we have this updated belief, what we still have to do is to act optimally, right? And so that means that the agent should pick the action which has the greatest expected reward, the largest expected reward. So for which this v-value is the largest when you start in the current state. The issue is that the agent does not know again in which environment it is in, right? So that means it should basically try to find the action which, if it could perform this action in all of this environment, then its expectation would lead to this largest reward, right? So for every environment mu in our set of computer programs, the agent must first take into account how likely it is that it is facing mu, given the interaction history so far and the prior probability of mu. So that's precisely what we would have computed with this posterior density. And then consider all possible future interactions that might occur, assuming, of course, that the agent would be optimal, right? Then we would have to, of course, evaluate how likely they are, and then select the actions that maximizes the total expected future reward. So concretely, the agent would need to solve this problem, this maximization problem. It would need to find the action A for which this quantity would be optimal. So there are a few things to unpack here. So first, we have to decide the action that we have to perform at time step t. So this is the notation AT. And we'll consider this action, and then everything else that we'll do afterwards, right? So we'll consider an infinite horizon of subsequent actions, and we'll assume, of course, that we keep being optimal, right? So we'll keep maximizing. So each one of these future choices will also try to maximize that same quantity. Each possible sequence of actions, right, will lead to a sum of reward or a discounted sum of reward, right? And all of them will be average depending on, because this would only be true for, this assumed expected sum of reward depends on one environment, but we would need to account for all possible environments, right? Remember that we don't know in which precisely we are, right? So we have to compute the weighted average of the total discounted reward across all possible Turing machines, meaning across all possible environments. And so this is what you would have in this last factor on the right, which itself would be defined this way. It's a weighted sum over all possible computer programs, all computer environments. And for each of them, you put a weight in green, which in this case is proportional to, which is your prior beliefs. It's that complexity, which depends on the complexity of the program, times the likelihood of the data that you've already observed so far, right? So this thing is proportional to your posterior beliefs. And that's what is giving you the weights to average all these discounted rewards together, right? So not only would we have to find the action which is optimal for one environment, we would have to find the action which would be optimal at once over all possible environments in expectation. So that's much more complicated than everything we've seen. And indeed, if you were to try to implement this thing, you would quickly notice that it's just incomputable. There is no way you would manage to compute any of these sums for m a time horizon which goes to infinity. And also we would have to solve this, to make these updates to obtain our prior beliefs. But this is the sum over all possible computer programs, and that's just a lot, and we have no idea how we could sample from this set in a way which would allow us to approximate this quantity. Okay, so that's a nice theoretical framework, and actually it's proven mathematically that this is optimal under many definitions of optimality. But unfortunately, it's quite impractical. It's even totally impractical because you would, at least we don't know any algorithms that we could use to be able to solve this optimization problem. However, what I wanted why I put this framework in today's lecture is because this framework, this formalism, provides a few interesting things when it comes to reason and understand AGI. So Erxi, you can view that as a high-level blueprint or some kind, or at least you could use it as inspiration for design. This is giving you a definition of exactly what we mean by an agent that would be optimal or that would be generally intelligent. Maybe there are other definitions, but this is a valid definition. It also provides the second benefit of this framework is that it provides a common terminology and also a precise formulation of the goal that we want to achieve. If we look, for example, at our previous definition, in which I said AGI is the intelligence of a machine that could successfully perform any this word I cannot tell it today. Any intellectual task that a human being can perform. This is quite vague and not very objective. What is an intellectual task that a human being can perform? So this is left for interpretation. However, this framework is defining, maybe you could argue about this definition, but it's providing a definition which is clear and objective. And so I can use this opportunity because there was the last question in the chat, which is about, is there a general test to prove if an AI is really an AGI? Again, if you look at our first definition, I think it would be quite subjective, and there is no test today. I mean, maybe you could use something resemblant to a Turing test, and if it passes, okay, fine, you could say it's generally intelligent, but as we have seen before, this test has problems in itself. So no, if we had a test, then we would have a precise definition of AGI, and that's something we do not have yet. Another benefit is that theoretical framework is really highlighting some of the fundamental challenges that we would need to solve in order to obtain an optimal and generally intelligent agent. And one of them would be to basically be able to navigate this huge space of actions across all possible environments. And that maybe would certainly, and that basically highlight the fact that we would need to precisely solve this exploration dilemma in order, for example, to grossly but reasonably approximate this optimal action. Because maybe we do not need to exhaustively and accurately solve this optimization problem in order to find an action which would be good enough or close enough to the optimal action. And finally, as I said already, it provides a definition of a measure of intelligence. It's very abstract. I will not argue against that, but it's a definition, and I think it's already interesting for that. All right. So now let's consider the second approach, which is maybe a bit more concrete and practical, which is this second hypothesis of artificial life. So artificial life is basically the study of systems. It's a field, it's a research field in itself, next to artificial intelligence. I would say it's broader than artificial intelligence. So it's the study of systems related to natural life, its processes, and its evolution through the use of simulations with computer models, robotic or biochemistry. And so basically one of the goals of this research field is to be able to synthesize, to reproduce life. And the goal of that, the purpose of this is to understand, for example, the origins of life, its development and its organization. And so follow-up questions to that would be, okay, we know we are the result of some evolutionary process that happened in nature, right? And we are intelligent beings, right? We are able to reason, to think, to dream, and other things like this. So we are intelligent beings. But the question is if we look back and consider that we result from some evolutionary process, from evolution, then the question would be, how did intelligence arise in nature? And how does it come that some creatures do not seem to be intelligent in the definitions that we give to intelligence, while some others are intelligent? Like if you compare, I don't know, a plant to a human, then you would not say that the plant is generally intelligent as we are, right? But what happened basically during this evolutionary process that some creatures came to be intelligent while others did not. And so the goal of this research field is basically to be able to reproduce or to replicate, resimulate some kind of evolutionary process in order to see this kind of toolkit emerge from it. So there are different approaches to artificial life. So you can have soft artificial life, which is basically to try to replicate evolutionary processes in terms of computer software. The second approach would be hard or hardware artificial life, in which you try to do the same but using, for example, robots. And finally, you have wet artificial life, which is an approach which tries to reproduce life using chemistry or biochemistry. And so I think this is quite interesting because this is taking the problem from the other way around, in the sense that, for example, if you look at what is done in AI and what we've seen together, is that we approach the problem from a top-down approach, from a top-down methodology. So we consider the problem, and then we try to divide the problem into sub-problems, and then find solutions for these sub-problems, and then we combine all these things together. Artificial life approaches, on the other hand, they all work from the bottom up. So what they are really interested in this community, in this research field, is to identify what are the key fundamental elements that you need to bootstrap the evolution process, and then you just let it run and see what would happen, right? And you hope that after many generations or a long time, then you would see cool things emerging from this process, like intelligent creatures. So I could talk for a few lessons about that. I will just show you first a video of some applications of some initial results of artificial life from biochemistry or from the biochemistry approach. And of course, since this is a computer science course, I will then mainly talk about software approaches. So this is a TED talk by Martin Ensvik. And the talk is titled "The Line Between Life and Not Life." And so this scientist and his group are basically trying to produce protocells, so synthetic cells that would resemble the kind of behavior you would have in a cell as we define it. And so it tries to basically reproduce that using sacks of chemicals, molecules that are all mixed together in some kind of primordial soup, and then you mix, and then you will see that quite interesting happen and emerge from this research. So let's see.
So we came up with a different protocell model, and this is actually simpler than the previous one. In this protocell model, it's just an oil droplet with a chemical metabolism inside that allows this protocell to use energy to do something, to actually become dynamic, as we'll see here. We add the droplet to the system, it's a pool of water, and the protocell starts moving itself around in the system, okay? Oil droplet forms through self-assembly, has a chemical metabolism inside, so it could use energy, and it uses that energy to move itself around in its environment. As we heard earlier, movement is very important in these kinds of living systems. It is moving around, exploring its environment, and remodeling its environment, as you see by these chemical waves that are forming by the protocell. So it's acting, in a sense, like a living system trying to preserve itself. We take the same moving protocell here, and we put it in another experiment, get it moving. Then I'm going to add some food to the system, and you'll see that in blue here. Right? So I add some food source to the system, the protocell moves, it encounters the food, it reconfigures itself, and actually then is able to climb to the highest concentration of food in that system and stop there, right? So not only do we have this system that has a body, has a metabolism, it could use energy, it moves around, It can sense its local environment and actually find resources in the environment to sustain itself. Now, this doesn't have a brain. It doesn't have a neural system. This is just a sack of chemicals that is able to have this interesting and complex lifelike behavior. If we count the number of chemicals in that system, actually, including the water that's in the dish, we have 5 chemicals that can do this. So then we put these protocells together in a single experiment to see what they would do. And depending on the conditions, we have some protocells on the left there that are moving around, and then it likes to touch the other structures in its environment. On the other hand, we have 2 moving protocells that like to circle each other, and they form kind of a dance, complex dance with each other, right? So not only do individual protocells have behavior, what we interpret as behavior in this system, but we also have basically population-level behavior similar to what organisms have. So now that you're all experts on protocells, we're going to play a game with these protocells. We're going to make 2 different kinds. Protocell A has a certain kind of chemistry inside that when activated, the protocell starts to vibrate around, just dancing. So remember, these are primitive things, so dancing protocells, that's very interesting to us. The second protocell has a different chemistry inside. And when activated, the protocells all come together and they fuse into one big one, right? And we just put these 2 together in the same system. So there's population A. There's population B, and then we activate the system, and protocell B's, the blue ones, they all come together, they fuse together to form one big blob, and the other protocell just dances around, and this just happens until all of the energy in the system is basically used up, and then game over. So then I repeated this experiment a bunch of times, and one time something very interesting happened. So added these protocells together into the system, and protocell A, protocell B fused together to form a hybrid protocell AB. That didn't happen before. There it goes. There's a protocell AB now in the system. Protocell AB likes to dance around for a bit. Well, protocell B does the fusion, okay? But then something even more interesting happens. Watch when these 2 large protocells, the hybrid ones, fuse together. Now we have a dancing protocell and a self-replication event, right? Just with blobs of chemicals again. So the way this works is you have a simple system with 5 chemicals here, a simple system with 5 chemicals here. When they hybridize, you then form something that's different than before. It's more complex than before. And you get the emergence of another kind of lifelike behavior, which in this case is replication. So since we can make some interesting protocells that we like, and they're interesting colors and interesting behaviors, and they're very easy to make, and they have interesting lifelike properties, perhaps these protocells have something to tell us about the origin of life on the Earth. Perhaps these represent an easily accessible step, one of the first steps by which life got started on the early Earth. Certainly, there were molecules present on the early Earth, but they wouldn't have been these pure compounds that we worked with in the lab and I showed in these experiments. Rather, they'd be a real complex mixture of all kinds of stuff, because uncontrolled chemical reactions produce a diverse mixture of organic compounds. Think of it like a primordial ooze, okay? And it's a pool that's too difficult to fully characterize, even by modern methods. And the product looks brown, like this tar here on the left. A pure compound is shown on the right for contrast. So this is similar to what happens when you take pure sugar crystals in your kitchen, you put them in a pan, and you apply energy. You turn up the heat, you start making and breaking chemical bonds in the sugar, forming a brownish caramel, right? If you let that go unregulated, you'll continue to make and break chemical bonds, forming even more diverse mixture of molecules that then forms this kind of black, tarry stuff in your pan, right? That's difficult to wash out. So that's what the origin of life would have looked like. You needed to get life out of this junk that is present on the early Earth 4.5 billion years ago. So the challenge then is...
All right, so I will not watch the full video with you, but if you're interested, just click on the link in the slides. But this was just to show you that there is research to try to reproduce, or at least I would say not maybe reproduce for the sake of reproducing, but trying to understand the origin of lives in the early Earth from biochemistry principles, and I think it's quite interesting. And already in this small video, you see that we start understanding what could have been the principles that led, that basically made the transitions between non-life, just molecules, to life-like molecules, or what you would say life in today's definition. And then, of course, what then led to intelligent creatures as we are. All right. The second approach that I will mention today is the software approach of artificial life. And another name for that is evolutionary algorithms. And so basically it all starts with this idea that you can view evolution or you can hypothesize evolution as some kind of unknown algorithm, right? And very simple algorithm. And this is an algorithm that gave rise to AGI because we are the result of this algorithm and we consider ourselves as generally intelligent creatures, right? So this is a proof that this is indeed possible in principle because we are there. And so that's the whole point of trying to simulate or re-simulate this process. And so that field, or that family of algorithms is basically based on the idea that we should try to simulate evolutionary processes in computers, because the hypothesis is that they should or they could, there are big question marks here, eventually reproduce lifelike creatures and then maybe intelligence. Of course, that will highly depend on the initial conditions that you put in this simulated world, but maybe that is indeed possible. So one of the most famous evolutionary algorithm is Conorway's game of life. Maybe you've seen that before. It's not really a game, but you should rather view that as some evolutionary process, which in this case is fully deterministic. It's defined by a very simple set of rules, which define basically what will be the next value of each one of these cells, given surrounding values. And so you could have black dots which become white dots, and vice versa, depending on the current state of the game. And from this very simple set of rules, you can actually define a complete world, which can be actually quite complicated, to the point that people have even proved that this simple set of rules led to an environment which is Turing complete, meaning that you can represent any computer program in this game as well as you could do in a regular computer language, right? So if you're interested, I would really recommend you to watch this this documentary. It's 15 minutes long, but I think it's quite interesting. But it's a bit out of the scope of this course. But I think it's still a very strong example of evolutionary algorithms, in the sense the sense that you would start with a very simple set of rules, and then again in this kind of bottom-up fashion, you can basically see the emergence of very complicated behaviors. And in this case, from a very simple set of rules, in the right initial conditions, of course, then you can basically reproduce anything which is as complicated as any computer program. So this is not life, of course, and this is not intelligence, but I think this is really a good demonstration of what could come out of this kind of approach. The main approach, which is closer to AI, is to view evolutionary algorithms as some kind of meta-heuristic optimization algorithms. And so that's a recipe which is quite simple and which basically try to mimic or to replicate the evolution as we view it. So you would start with a random population of creatures, right? And so this is, remember, this is a computer program. You have the freedom as the programmer to basically define the environment, the world, and the creatures and how they are defined. So this is very abstract for now. I will show you a few examples afterwards. So you would start with a random population of creatures. They could be very simple or already quite complicated. That's another freedom you have when you deal with simulated environments. And then you repeat the 4 following steps for as long as you want, right? And at each iteration, what you should do is that you basically assess the goodness or the performance of each creature to perform a given task. So that task could be, for example, to swim as fast as possible in the environment, or simply just to stay alive, right? Then the second step would be to select the creatures which are the fittest. So among all the creatures for which you have tested for which you've evaluated their performance, you select the best ones, and you will select them for reproduction. And then reproduction is defined in the third step. So you would basically produce or breed new creatures by combining and mutating the virtual genes that define the selected parents. So for example, you pick two of the best creatures, they would themselves be defined in some way, and that way I call that the virtual genes of the creatures. For example, if the creatures concretely are implemented as neural networks, well, you could try to breed new creature by combining the neural networks of the two parents. But that's something that you can do, and that works actually quite well. And then finally, in the fourth step, what you would do is that you would basically kill or remove the least fit creatures of the population with the new ones that you've created in the previous step. And then you would repeat this loop until termination. And the idea, or the interesting thing that you would see if you execute this kind of algorithm, is that as this cycle of variation and selection continues, creatures will become more and more successful to the task that you have defined, for solving the task that you have defined. And it's very interesting because you really see the emergence of this kind of very complicated behaviors. So this whole field of, I would say, evolutionary algorithm started in 1994 by Carl Sims, which already, 25 years ago, 26 years ago, produced this video and this scientific paper in which he showed virtual creatures which he evolved from using this evolutionary algorithm.
Physical environments. Swimming speed was used to determine survival. Most of the creatures are results from independent evolutions. Some developed strategies similar to those in real life. Once they're evolved, multiple copies of these creatures can be made and simulated together in the same environment. The next group of creatures were evolved for their ability to move on a simulated land environment with gravity and friction. Some simple solutions with just two parts were found. Some seemed like they could use some assistance, while others were fairly efficient, such as this rowing-like behavior. Here is an odd cousin of the previous. A mutation caused him to tumble. Some creatures evolved to incorporate contact sensors in their control systems. Here is another inchworm-like.
So I will just pause the video for now, just to stress that that same kind of task, like for example motion or moving or swimming, given the body of these creatures, is something we have already solutions for. You could use, for example, any kind of reinforcement learning or kind of algorithm we've seen together, and that would be sufficient to find a policy for which you would obtain a high reward. And so that means that the creatures that you would have that would be associated to this policy would have good performance as you would measure them in these evolutionary algorithms. So the approach here is not to postulate any kind of Q-learning or whatever algorithm. It's just to follow this very simple recipe. The only thing that you specify concretely is how you measure goodness, how you measure fitness to perform a task, and then you just let the optimization algorithm, the evolutionary algorithms go on for generations, for maybe thousands or more generations. And then you look at what you get as the outcome of the algorithm, right? And these are some of the creatures, virtual creatures, that emerge from this process.
Systems. Here is another inchworm-like creature that tends to go in circles. This was actually a creature first evolved for its ability to swim in water, then later put on land and evolved further. A successful sidewinding ability resulted. Here is one with a hopping style. The protrusions on its arms seemed to help prevent it from tipping over. This was the fastest, with a successful galloping-like stride. This group was evolved for their jumping ability. This group was evolved for their ability to adaptively follow a red light source. The resulting creatures are now being interacted with. A user is moving the light source around as the creature behaves. This one seems to flail randomly, but somehow still manages to approach the light. Perhaps it is mean to move the goal away just as it arrives. Here is one that has propeller-like fins which are tilted depending on the direction of the light. It can adaptively swim up or down very well. This final group of creatures was evolved for their ability to compete for control of a green cube. The creature closest to the cube at the end of a simulation is the winner. Here, a strategy first arose for simply tumbling towards the cube. Then one learned to block out his opponent. But then later one learned to overcome the obstacle by climbing over it. Some pinned down their opponents. Some covered the cube with protective arms. Others simply unfolded onto the cube. The success of a strategy is often highly dependent on the opponent. Here is a hockey-playing creature, which takes the cube away and wins by a large margin. Here are two similar hockey strategies battling it out, with appropriate gestures. This crab-like creature walks well, but often continues past the cube and instead seems to prefer beating up on his opponent. Against the arm, the crab seems to simply walk away. A successful strategy is this two-arm technique that swipes quickly in from the side and moves the cube over to a second arm. These are the final rounds of competition amongst the overall best. Finally, the seeker arm goes against the side swiper, but the cube is just out of reach.
All right, so we get the idea. So it's 25 years old, of course. We've made progress since then. So this is another video from last year. So first of all, I would also want to stress that these approaches using evolutionary algorithms are not as mainstream, of course, as the kind of approaches, the kind of algorithm that we've seen together. But you see them being used more and more, maybe not following the recipe that I've shown you, but in combinations to algorithms that we have seen. And so when you start merging these two approaches, when you start basically to, for example, combine learning algorithms with evolutionary processes, then you get quite interesting solutions usually. So this is another video from UC Berkeley from last year. I will not show it, but it's an example more recent of how you can derive agents that are able basically to move by themselves, to implement efficient motion in environments. Again, using evolutionary processes. And in this video, they explicitly compare with the kind of policy you would obtain if you were to follow a vanilla reinforcement learning algorithm, and in which they show that it would not work as well as this kind of approach. If you're interested and curious, I also invite you to watch this mini documentary about artificial life. Here I will just quickly jump.
My name's Dave Ackley. I'm in the computer science department at the University of New Mexico.
Of evolutionary processes, evolutionary algorithms, or agents that are trained with this kind of algorithms. So here you have an agents that have to basically control a body in order to move as far as possible, let's say. Right, so you can watch the video longer. I think it's quite interesting. And finally, this demo, I think it's also quite interesting. So let me open it. So what you see there is just a small program running JavaScript in my browser, in which you have these creatures with these two eyes, and each of them is basically controlled by a neural network of the same kind that we have seen together in lecture 7. And that neural network is basically getting as input some information about the state of the creature, and more specifically about how close they are from these planks. And unfortunately, if the creatures eat the planks, then they die. And so what you would basically want to certainly obtain or derive as a policy is a policy in which the creature would not die, and they would necessarily have then to derive that they should try to avoid as much as possible being close from these planks, because otherwise they would die. And so this is the kind of policy that you would get as creatures die and are bred together through this evolutionary process. I can add a few more creatures if I want. How did I change that? I don't know. Can also draw planks to kill. How did I? Oh, like. So if you let it run for long enough, you would see that after a few hours, you would be left with a set of creatures which are quite good at avoiding the planks, because they are the result of the natural selection of the creature which survived, and they precisely survived because they were equipped with a neural network which led them to avoid and to move away from the planks. But that's something which is not explicitly programmed. You just let the simulation run, and in this case the only criterion that you use, the only fitness function that you use, is just that actually there isn't any really. Creatures just die after some time, and they can replicate, I suppose, if they bounce onto each other, and that's it. So there is really no explicit fitness function. Everything would be discovered by the evolutionary algorithm in itself. All right. So let me close this. So of course you would be correct and right in telling me that this is too simple. How could it lead to creatures that are generally intelligent? And I would completely agree with you. And the reason is that, of course, or of course I don't know, but an hypothesis for this to be true would be that you need to put the creatures in an environment which is complex enough in order to lead to the emergence of these behaviors. Because in this case, in this simple world, if you avoid the planks, then that's enough and you will survive. But you don't need to, you don't need the emergence of a whole cognitive toolkit in order to survive, because that's not necessary in this too simplistic environment. And so one hypothesis is that for the emergence of AGI, you would need environments that in some way incentivize the emergence, as I said, of a cognitive toolkit, like paying attention to things, to memorize what happened before, to be able to represent knowledge, to reason, to have maybe emotions like fear, to be able to forward simulate, to anticipate what would happen, also to encourage the acquisition of skills. And so the environments in which you run these evolutionary algorithms is quite important if your goal is to work towards AGI. If on the other hand you just want to find policies, agents that would solve quite well a specific task, then this algorithm would work, but they would not be able to generalize again, right? So this is in a sense moving away the problem to something else, which is not what you should put in the agent, but what you should put now in the environment in order to bootstrap the system with what is necessary for the emergence of this toolkit. And there are many question marks here, but that's an hypothesis, and I think that's correct. Also, maybe you should consider environments which are multi-agents from the start. And I think they are indeed certainly better, because if you have not only one agent in the environment, but many of them acting together and jointly, then that means the optimal behavior will depend on the current behavior of the others, right? And so that means the optimal strategy will change from one generation to the next dynamically. So it would lead certainly to some kind of natural curriculum. So that is to say that basically the difficulty or the complexity of the environment will be determined by the skills of the other agents. And so if you have, for example, if you look, for example, in wildlife, you may have predators and prey, but you can quickly understand that the skills that are required for the prey to survive highly depend on their predators. So if the predators are not smart enough, then you don't need the prey to be smart as well. Right? But so there is this adjustment and this equilibrium which happens in which, it's not really an equilibrium, it's really a continuous adaptation of the skills that you need to survive in the environment. So that's something which is also certainly necessary if we would be serious at trying to run these evolutionary algorithms for long in order to see the emergence of complicated behaviors, is that we would need environments which are multi-agents, because they would encourage these two properties, variety and natural curriculum. All right, so that's basically it for AGI. I will not say more about that today. I think you understand that this is just a big question mark for now, but we have some maybe elements of algorithms or approaches that could maybe lead to that, but this is still very speculative for now. Nevertheless, when it comes to evolutionary algorithms, I would still want to stress that these algorithms may still be you can use them maybe to someday implement AGI, but you can also use them today to find policy which are good to solve a specific task. And this is precisely the kind of things you see in this kind of research, where the task is well defined. We want to move. We want to equip an agent with motion capabilities. We don't know how to do that, but we just let the evolutionary algorithm find a good policy for us. And that's something that works already today. All right. So now let's come to the conclusion for the course. I will first start by showing you a video, another TED Talk. It's a bit long, it's I think 15 minutes long, but I think it's a good summary of my opinion about how you should view artificial intelligence as a field, and as a field which will change basically technology and many other disciplines in the future. And it's basically a position in which we should not oppose artificial intelligence to something like you may have this view that artificial intelligence will steal your job and will replace all humans. I really don't agree with this opinion. Rather, you should see, I think, AI as a way basically to augment humans with new capabilities in order to solve huge, big challenges that we face, like climate change, scientific problems, medical problems. I think all of these fields would really benefit in using more of artificial intelligence, and I'm quite sure they will quite soon do that. And so this is a view talk by Garry Kasparov, who was a world champion at chess, and is quite known because he made this match in the 90s against Deep Blue. So Deep Blue is a computer program that basically beat him during that time. And it's really also the tipping point where people started to realize that these algorithms, they start to be better than humans, and therefore and therefore eventually that means we would be replaced by these machines. And this is not his opinion at all. And I think so. I will let you watch the video, and then we'll come back in 15 minutes.
This story begins in 1985, when at age 22, I became the world chess champion after beating Anatoly Karpov. Early that year, I played what is called simultaneous exhibition against 32 of the world's best chess-playing machines in Hamburg, Germany. I won all the games. And then it was not considered much of a surprise that I could beat 32 computers at the same time. To me, that was the golden age. Machines were weak, and my hair was strong. Just 12 years later, I was fighting for my life against just one computer in a match called by the cover of Newsweek, The Brain's Last Stand. No pressure. From mythology to science fiction, human versus machine has been often portrayed as a matter of life and death. John Henry, called the still driving man in a 19th century African-American folk legend, was pitted in a race against steam-powered hammer bashing a tunnel through a mountain of rock. John Henry's legend is a part of a long historical narrative pitting humanity versus technology. And this competitive rhetoric is standard now. We're in a race against the machines, in a fight or even in a war. Jobs are being killed off. People are being replaced as if they had vanished from the earth. It's enough to think that the movies like The Terminator or The Matrix are non-fiction. There are very few instances of an arena where the human body and mind can compete on equal terms with a computer or a robot. Actually, I wish there were a few more. Instead, it was my blessing and my curse to literally become the proverbial man in the man versus machine competition that everybody is still talking about. In the most famous human-machine competition since John Henry, I played 2 matches against the IBM supercomputer Deep Blue. Nobody remembers that I won the first match. In Philadelphia, before losing the rematch the following year in New York. But I guess that's fair. There is no day in history special calendar entry for all the people who failed to climb Mount Everest before Sir Edmund Hillary and Tenzing Norgay made it to the top. And in 1997, I was still the world champion. When chess computers finally came of age. I was Mount Everest, and Deep Blue reached the summit. I should say, of course, not that Deep Blue did it, but its human creators, Anand Tharman, Campbell, Horn, Su, hats off to them. As always, machine's triumph was a human triumph, something we tend to forget when humans are surpassed by our own creations. Deep Blue was victorious. But was it intelligent? No. No, it wasn't. At least not in the way Alan Turing and other founders of computer science had hoped. It turned that chess could be crunched by brute force once hardware got fast enough and algorithms got smart enough. Although by the definition of the output, grandmaster level chess, Deep Blue was intelligent. But even at the incredible speed, 200 million positions per second, Deep Blue's method provided little of the dreamt of insight into the mysteries of human intelligence. Soon, machines will be taxi drivers and doctors and professors, but will they be intelligent, quote unquote? I would rather leave these definitions to the philosophers and to the dictionary. What does really matter is how we humans feel about living and working with these machines. When I first met Deep Blue in 1996, in February, I had been the world champion for more than 10 years. And I had played 182 world championship games and hundreds of games against other top players in other competitions. I knew what to expect from my opponents and what to expect from myself. I was used to measure their moves and to gauge their emotional state by watching their body language and looking at their eyes. And then I sat across the chessboard from Deep Blue. I immediately sensed something new, something unsettling. You might experience a similar feeling the first time you ride in a driverless car, or the first time your new competitor manager issues an order at work. But when I sat at that first game, I couldn't be sure what this thing was capable of. Technology can advance in leaps, and IBM had invested heavily. I lost that game. And I couldn't help wondering, might it be invincible? Was my beloved game of chess over? These were human doubts, human fears, and the only thing I knew for sure that my opponent, Deep Blue, had no such worries at all. I fought back after this devastating blow to win the first match, but the writing was on the wall. I eventually lost to the machine, but I didn't suffer the fate of John Henry, who won, but died with his hammer in his hand. It turned that the world of chess still wanted to have a human chess champion. And even today, when a free chess app on the latest mobile phone is stronger than Deep Blue, people are still playing chess, even more than ever before. Doomsayers predicted that nobody would touch the game that could be conquered by the machine, and they were wrong, proven wrong. But doomsaying has always been a popular pastime when it comes to technology. I learned from my own experience is that we must face our fears if we want to get the most out of our technology. And we must conquer those fears if we want to get the best out of our humanity. While licking my wounds, I got a lot of inspiration from my battles against Deep Blue. As the old Russian saying goes, you can't beat them, join them. And I thought, what if I could play with a computer, together with a computer at my side, combining our strengths? Human intuition plus machine's calculation. Human strategy.
Right, so sorry about that. I was just notified that the stream was blocked because I was streaming the video myself, which is copyrighted. Apparently that's automatically blocked. Right, so yeah, unfortunately we won't be able to watch it to the end, but I really invite you to watch it until the end. I really share his opinion, and I think it's a really positive opinion about how you should view progress that will be enabled by artificial intelligence in general. And this is also how I wanted to conclude the course, by again saying that we have seen together quite a few algorithms, quite a few approaches, and we have used Pacman as illustrations of what you can do, or at least or to better understand how this algorithm works. But of course, you should see much beyond Pacman, and this is my message for you. Pacman is just a pretext, and of course, you should aim as engineers and computer scientists to use artificial intelligence to solve much more interesting problems, and you'll find plenties in what you will do in the futures, in science, in engineering, in society. There are plenties of opportunities to use artificial intelligence algorithms, and they are already transforming these fields. And so as future engineers and scientists, I think you should view AI as some way, as a new tool which offers you opportunities to address some of the world's biggest challenges. Climate change is of course one of them. Health problems like the current coronavirus crisis, and plenty of others. And I think you should seize them and really basically think out of the box and be confident that you can address these challenges with what you've learned or what you've discovered and will continue to learn about AI, and of course in your follow-up classes. All right, so that was my final word. I also want to just do a quick recap about what we've seen together. We had 11, 12 lectures together for 3 months. We've covered quite a lot. Maybe I will use this map instead. So we started with a broad definition of AI, from which then we define intelligent agents, and then we forked into 2 directions. First, how to basically build agents to solve problems using search algorithm, and then second, how to reason under uncertainty. And so we've seen together how to represent uncertain knowledge, how to do inference in Bayesian networks, how to reason over time, and also how to improve itself with learning algorithms. And then finally, we've put all these pieces together, first to define Markov decision processes to make decisions under uncertainty, and then finally, how to also be able to do that when the environment is unknown. And so that meant that we had to also learn about the environment while acting in it, and that led to reinforcement learning. And then last week I took this example of communication as just example of applications that you can do with AI today. And finally today we concluded with AGI. If you've been interested by this course, then you should know that it was really designed as an introduction to the many other courses that you can find in the course program of the university. So in your master, you will get, for example, access to Introduction to Machine Learning. We have quite a few actually courses on machine learning. So Introduction to Machine Learning is given by Pierre Gers and Louis Wenkel. And then we have Advanced Machine Learning, which is more like an introduction to research, in which we read and discuss scientific literature. It's given by Pierre Gers, Louis Wenkel, and myself. And then there is this third course on deep learning, which I'm giving, in which we only talk about neural networks. We have also Optimal Decision Making for Complex Problems, given by Damien Ernst, in which you cover reinforcement learning, of course in much more details than what we've done together, because there is so much more to learn about that. There are also a few classes which are more applied, I would say. So you have a few courses on robotics. The closest to AI, I would say, is Introduction to Intelligent Robotics, in which you see, again, algorithms like planning, filtering, and all these things, but really applied for the goal of building intelligent robots. Knowledge representation, this one will disappear, but will be replaced next year by a new course. I will just keep it. Computer vision, given by Mark van Drogenbroek, in which you see families of techniques to tackle computer vision problems, including some deep learning approaches. And then there are also a few other classes which are maybe not as directly connected as to AI as the others, but I think which are worth mentioning, like information encoding theory or large sample analysis, in which methods like MCMC, which we've talked about in one of the lectures, are covered. Finally, there are also other classes, less technical, one of them given by the Faculty of Law about the introduction, which is about the introduction to the law of robots. So like more societal and ethical impacts of artificial intelligence, robots, and these things. And I think it's good also as engineers and computer scientists that you, of course, you should know about the technical details of AI, but it should go beyond that. And I think having this kind of courses is really good for you. All right. Finally, I also want to say that if you want to maybe explore research in AI, then you should know that we have some opportunities in our group. So broadly at the Montefiore department, with me, but also with a few other colleagues. So for example, if you are looking for summer internships, feel free to contact us. If later on you are looking for master thesis opportunity, travaux de fin d'études, feel free to contact us. And also if maybe considering a PhD is something you have in mind, then feel free also to contact us to discuss about that. With that, I really thank you all for following this course, Introduction to Artificial Intelligence. This is the very last slide of the course. I really hope you have liked the materials and everything we've talked together. It's really unfortunate that I've not seen any one of you this year. I talked to my wall for 3 months. That's a bit sad, but I think I will see you in January for the exam. It should happen in a real and physical amphitheater where we'll have the opportunity finally to see each other. All right, so thanks again and goodbye.